Dear students, welcome. This is the second video of lecture 2. We are still talking in lecture 2 about force vectors. We provided a quick summary about the difference between vectors and scalars, and we talked about multiplication of vectors with a scalar and then addition of vectors. Now we want to go a little bit more into vector analysis and talk about resolution of vectors. Two common problems in statics involve either finding the resultant force, assuming that we know the components, right? And the second one is resolving a known force into two components, just reversing the first process. So resolution of vectors is actually breaking up a vector into two components if we are dealing with vectors in 2 dimensions, and breaking the vector into 3 components if we are working in a 3-dimensional system. Start with the image that you see in the screen in A. So you have a vector, and then on B we broke it down into FU and FV on 2 different axes. Actually, it's kind of like using the parallelogram law but in reverse, because you know that FU plus FV should give you F, the resultant force, which is the diagonal of the parallelogram. C represent also the same thing, FU plus FV, resulting in F, using a schematic representation or the graphical representation in the triangle method. This is resolving a vector into 2 different components. This is very important. So why do we need resolution of vectors? The answer to that is addition of system of coplanar forces. We cannot use a parallelogram law because it will be complicated. So the easiest way to do, if you have a system of 10 vectors or 20 vectors, you can break down each of those vectors into 2 components, and then we can add the components in the directions. Let me elaborate more and explain this a little bit more. Sometimes it's necessary to resolve a force into 2 components in order to study its pulling or pushing effect in 2 specific directions. If you remember something about the Cartesian coordinate system, if it's in 2D and 3D, you have X, Y, and Z axes. So when a force is resolved into 2 components along the X and Y axis, the components are then called rectangular components. So let's look at the image on the figure that we're looking at in A. So you have your force F in blue, but what if I'm interested in seeing what is the effect of this force along the X axis, which is this Fx, or if what I'm going to study the effect of this force on the y-axis. So imagine if you're studying a projectile and you want to see how far that projectile can go horizontally or vertically. So you're interested in a specific direction. That's why it's important we understand resolving vectors in different axes. In general, this is called the rectangular component method, which is how to resolve vectors on axes. For analytical work, we can represent the components of one or 2 ways. So if you want to resolve a vector on x and y, you can use something called the scalar or the Cartesian vector notation. Let's hold on to the scalar notation and let's focus on the Cartesian vector notation. So if you look at here, so we resolve vector on the image or the schematic that we're looking at. We can resolve vector into 2 components using the x and y axes coordinate system. Each component of the vector is shown as a magnitude and a direction. So the magnitude is the fx and the direction is either I or j. And those I and j are the directions are based on the x and y axes, and we use I and j, which are unit vectors. They're unitless and have magnitude 1 to designate the x and y axes. So if I want to see what's the effect of f on the x axis, I need to find the fx component, and I can add the I to represent that this is what is happening in the x axis horizontally. Now, the resultant of several coplanar, so coplanar means that they are on the same plane. So this is a 2-dimensional plane, so they are coplanar vectors. We're going to come back to this when we study 3 dimensions, because this is very critical. So the resultant of several coplanar vectors can easily be determined if the x and y coordinate system is established and the forces are resolved along these axes. It makes our life way much easier when we analyze complicated complex systems in 2 dimensions. Let's talk more about adding several vectors. So let's apply this tool in adding a lot of vectors, and how can this be accomplished? Remember, if more than 2 forces are to be added, we can use the parallelogram law However, it requires extensive geometric and trigonometric calculations. So if you have 20 vectors, you need to start with 2 and then the resultant be added to the third and then keep moving along the way. It's time consuming and you can make a lot of mistakes. So instead, we can use the rectangular component method, and that's step 1 is to resolve each force into its component. So if you have, as shown in our schematic to the left, top left, F1, F2, and F3. So you'll take F1, you need to break it down, resolve it into 2 components, F1 on the x-axis and F1 on the y-axis. Perfect. F2, you take also, you resolve it in 2 components, F2 on the x-axis and F2 on the y-axis. Same thing goes to F3. However, you need the angles. They're very important in order to do the projection or to resolve them on these axes. After you break down each force into its component, x and y component, you remove the forces, the original one, F1, F2, and F3, and you just deal with the F1x, F1y, F2x, F2y, F3x, and F3y. Pay attention to the direction of each force. Step 2 is to add all the x component together, and then you add all the y components together. You end up with only 2 forces, the FRX and FRY. That's to your right, the bottom of the screen. And step 3 is to find the magnitude and the angle of the resultant force. So you know that you have only 2 components, FRX and FRY, and you need to find now the resultant FR and the direction, which is theta, the angle. The x and y components of the resultant force are simply the algebraic addition. So if you have 3 forces, we're just adding the components of all the other forces, and then you end up with the schematic to the right, where you have an x component and the y component. You need to find the resultant. Okay, so let's show this process as an example. Just let's break it down a little bit more and just put some context into what we said and the mathematical representation. So if we want to find FR, which is the resultant force, we have 3 forces, F1, F2, and F3, and that's your schematic to the top left. You need to break each one of these forces into its x and y component. So you have F1xi and F1y, and you add I and j. Adding the i's and j's is just to make sure that you understand which one of the x-axis and which one of the y-axis. If we resolved F1, you know that you have F1x as positive because it's on the positive x-axis, and F1y positive because it's the positive y-axis. That's very important because you need to keep in mind your notation, the sign notation. What is your positive and what is your negative axis? Your x component of the F2x is actually on the negative x-axis. So you need to assign a negative sign for that thing. However, F2y is on the positive y-axis, so it stays positive. For F3, your y component is directing down, which is the negative y-axis. So F3y is negative, but F3x is positive because on the positive x-axis. And you just put the resolution, the projections, you put the i's and j's, and you put the notations for the sign notations, and then you add the x components together and the y components together, and you end up with FRX and FRY, the 2 components, and then you can find the magnitude of R and the direction theta for these forces. This is way much simpler than using the parallelogram method. So we started with 3 forces and we ended up with 2 components, one on the x-axis and one on the y-axis, I and j. So how can we determine the direction and the magnitude and the direction of these 2 forces, or the FRX and FRY? So to do so, the resultant vector can be represented by a magnitude and a direction, which is an angle theta. And how to calculate this? The magnitude of the resultant force is determined from the Pythagorean theorem. And when the resultant components are sketched, FRX and FRY, sketched on the x-axis and the y-axis, the direction theta can be determined from the trigonometry. If you have FRX and FRY and they are on the positive direction of each axis, the resultant FR is the square root of FRX square plus FRY square. That's the Pythagorean theorem. And you can find theta as the tan inverse of the y component divided by the x component. So FRY divided by FRX, the absolute value. And we will talk in the class when we meet in person of how can we implement this if the components are on negative axes, not the positive axes. So we'll solve a couple of problems about that. All right, this is the end of lecture 2. I know I promised you to talk about the dot product, but there's a lot of things to cover and I don't want to make the videos longer than 10 minutes or 11 minutes.